Every major quantum computing lab on Earth is chasing the same number, not qubit count, not clock speed. One ratio: does adding more qubits make your errors go down? The Zuchongzhi 3.2 team just reported that theirs does, by a factor of about 1.4 for every step up in code size. That word "reported" is doing real work in that sentence, and by the time you understand why, you'll know exactly what this result proves and what it doesn't. Before you read 1.4 as a victory lap, there's a harder question buried inside it. A factor of 1.4 across the first few steps is exactly what you'd expect if things are going well. The question is what happens further up the curve, at distances nobody has published data for yet. If the curve holds all the way there, fault-tolerant quantum computing stops being a theoretical promise and becomes an engineering project. If it bends, it joins a long list of encouraging early results that quietly stalled, and that list is longer than most coverage admits. By the end of this, you'll understand what a suppression factor actually measures, why the first points on a suppression curve are the easy ones, and what would have to be true for this result to mean what the optimists say it means. Because this isn't really a story about one chip or one lab result. It's about which side of a bet the next 5 years of global quantum investment will be placed on, and why both sides have real evidence. First, a quick sanity check on the number itself. 1.4 doesn't sound like much. It doesn't need to. It needs to compound. If a 1.4 suppression factor held across 10 steps up the code distance ladder, your logical error rate at the top would be roughly 30 times lower than at the bottom. That's not incremental. That's the entire mechanism by which fault tolerance becomes possible. The question is whether it actually compounds, or whether the curve that looks exponential at the start flattens out before it gets you anywhere useful. To understand why, you need to know what error correction is doing here. A quantum computer doesn't just run on qubits. It runs on logical qubits, which are built out of many noisy physical qubits stitched together with a layer of error-correcting code. The idea is that the redundancy lets you detect and fix errors without directly measuring the qubit, which would destroy the quantum information you're trying to protect. The surface code is the dominant approach. You arrange physical qubits in a grid, use neighboring qubits to check each other, and infer where errors happen from the pattern of those checks. Code distance is roughly the size of that grid. Distance 3 means a 3 by 3 arrangement. Distance 5, 5 by 5. Each step up multiplies the number of physical qubits per logical qubit. And in theory, each step should buy you a fixed, multiplicative improvement in how well the logical qubit is protected. Think of it like insulation in a wall. One layer reduces heat loss by a meaningful amount. 2 layers reduces it more, but not twice as much because heat finds other paths once the main channel is blocked. Gaps around frames, windows, structural bridges. In quantum error correction, the first layers of redundancy catch the obvious, simple errors. The harder errors, ones that slip through multiple checks at the same time, only become visible once the easy ones are already suppressed. That second class of errors is exactly what makes a 1.4 factor measured at small code distances an incomplete story. And it's what the Zuchongzhi 3.2 result has not yet had to answer for. What the team actually showed is this. Across the code distances they tested, each step up in code distance produced roughly a 1.4 times reduction in logical error rate. That's the right direction, the right shape, and a healthy factor. It means their physical error rates are below the threshold that makes error correction help rather than hurt. Below threshold is the prerequisite, not the achievement. And it means the code is doing what it's supposed to do at those distances. That is not a small result. Several well-funded teams have struggled to demonstrate clean suppression at all. The Zuchongzhi 3.2 team is doing the right experiment and getting a coherent answer. Whether anyone outside that team has confirmed the number is a separate question, one the public record doesn't yet resolve. The result is a team claim at preprint level, and that asterisk matters for a specific reason. The central claim is a slope, and slopes measured over a handful of points invite scrutiny. The floor in reliability is rising. The question is what's waiting to push back as it rises further. At small code distances, the dominant errors are single qubit errors. A qubit flips, or its phase rotates, and the surface code catches it cleanly because that's exactly what it was designed to handle. Scale up, and 3 other classes of error start to assert themselves. Crosstalk. Qubits influence each other's quantum state through electromagnetic coupling. More qubits means more neighbors, more unwanted interactions bleeding across the grid. Think of neighbors in a quiet apartment building. At 3 units, fine. At 30, somebody's noise is always getting through the walls. Leakage. Superconducting qubits have energy levels beyond the two states they're supposed to occupy, and a qubit can drift into a non-computational state that the error-correcting code has no way to handle, because the code was written assuming your qubits live in two states, not three. Correlated faults. Two or more errors happen close together in space or time, mimicking a pattern the decoder interprets as a single, correctable error, when it's actually two errors landing in a way that fools the whole system. Each of these becomes more statistically likely as you add qubits. They are not the error sources that set the 1.4 factor at the distances tested. They're the error sources waiting at distance 11 and distance 15. Can you engineer around them? Some teams use active leakage reset circuits. Some use better qubit isolation geometries. But every mitigation costs something. More calibration time, more physical qubits per logical qubit, more complex decoders that introduce their own failure modes. The floor doesn't keep rising for free. This is not the first promising suppression curve in quantum error correction. In 2023, Google published a peer-reviewed paper in Nature demonstrating logical error suppression increasing with code distance on their Sycamore processor, a landmark, independently verified result. The pattern across the field is consistent. Early code distances behave well, the slope looks encouraging, and the harder question, does the slope hold across 5, 6, 7 more steps, has not been definitively answered by any team, including Google, for the distances that practical computation would require. Zuchongzhi 3.2. Quote S result sits at the same stage of that question. It's promising. It is not a proof. The honest comparison between Zuchongzhi 3.2, quote S, 1.4 factor, and what Google or IBM have shown at equivalent distances cannot be made precisely right now, because the specific code distances the Zuchongzhi 3.2 team measured and the suppression factors Google and IBM reported at those same distances are not publicly available in a form that allows a direct apples-to-apples ranking. That's not a dodge. It's the actual state of the evidence. What the result allows you to say is that Zuchongzhi 3.2 is in the conversation. What it doesn't allow is a competitive ranking. So here's what the evidence actually permits. The Zuchongzhi 3.2 team is demonstrably operating below the error threshold for the code distances they tested. Their suppression factor is a real, positive, physically meaningful result. What the evidence doesn't permit: any extrapolation to larger distances without more data, any claim of fault tolerance. Fault tolerance means driving logical error rates low enough for real computation, which requires many more steps up the distance ladder than have been demonstrated by anyone. Any direct competitive ranking without equivalent distance-by-distance comparison. And the result needs peer review. It needs replication at larger distances. Both take time, and the slope measured over a few early points is exactly the kind of claim that peer review and replication are designed to test. Here's my honest read. The triumphalist version, China has cracked error correction, isn't supported by what's in the public record. Neither is the dismissive version. This is just a preprint. Ignore it. A preprint in physics carries real information. It carries it with an asterisk. And the asterisk matters more here than in most results because the thing being claimed is a slope. And a slope needs more points before you know whether it's a trend or a coincidence of early data. What I think is true is narrower and more interesting than either extreme. This result shifts the odds, not the conclusion. The odds. A clean 1.4 factor at the tested distances means the physics is cooperating. The Zuchongzhi 3.2 team is running the right experiment, measuring the right thing, and getting a coherent answer. That matters. What it doesn't settle is whether the engineering will cooperate at the distances where the hard errors assert themselves. The floor is higher than it was. Whether it keeps rising or plateaus as crosstalk and leakage and correlated faults find their footing is the only question that matters from here. Every team in this race is trying to raise the same floor. Take noisy physical qubits and build, step by step, a more reliable logical layer above them. Zuchongzhi 3.2 just showed their floor is rising at the rate the theory demands, for the distances they've tested. The bet is whether that rate survives the distances they haven't. So here's what I want your honest read on. Bet A, the 1.4 factor is real signal. The curve will hold. The hard errors won't assert themselves any faster than engineering can handle them, and China's fault tolerance path is now an engineering scale-up problem rather than a physics problem. Bet B, early curve points always look clean. The hard errors haven't shown up yet, and a 1.4 factor at the distances tested tells you less about distance 15 than the optimists say. Which bet would you back? And what would change your mind? Tell me in the comments, because that question is genuinely open and both sides have defensible ground. If you want to follow exactly how this curve holds or bends as larger distance data comes in, and what it means for who's actually leading the fault tolerance race, subscribe, because that's the specific story worth tracking. One curve, one factor. Whether it holds is the only question left.